Hello, this is Dr. Scott Denstead, founder of EZWxBrief, your best online source for aviation weather and education. Welcome to episode 26 of EZWxChat, a program to discuss various topics related to aviation weather. Again, welcome back everybody to this next episode of EZWxChat. And if there are folks out there that have enjoyed the last 25 episodes, would certainly love to have you tell other folks about this educational opportunity. So get in your email, texts, aviation forums, and blast out information about this particular opportunity for learning more about weather. So in this episode, we're going to focus primarily on satellite imagery. And specifically, I want to look at the infrared satellite imagery. And in the EZWxBrief application, you can get to the imagery by clicking on the Start button and going to View Static Weather Imagery. And so at the highest level, the very, very highest level here, when we think about imagery in terms of satellite-based imagery, the actual sensors themselves come in a couple different flavors. The sensor we're talking about here is the satellite itself. There are essentially geostationary satellites, and they are low Earth orbiting satellites, or what are sometimes called polar orbiting satellites, that can pick up information from the Earth and essentially send that down to the ground where it can be examined by forecasters and folks like you and I. Now the low Earth orbiting satellites, or polar orbiting satellites, essentially will produce a more striped or bandit effect because it's going around at a much lower altitude. But the advantage there is that it's really closer to the actual weather, the clouds that are out there, and can pick up a lot more details being close in. However, it is a more narrow band that comes across. Let's say it may pick up the entire eastern half of the U.S., or maybe the central or plains area in the U.S., and it's going to pick up that information all the way around the Earth. And then they can stitch that together after a few orbits and produce a more, let's say, it'll be still disjointed because we know that weather moves with time, but nevertheless it will still be somewhat of a kind of a U.S.-based or a North American-based picture, but again broken up into these multiple bands. Now the other satellite that we see are what is essentially called geostationary satellites. And so these geostationary satellites, they circle the Earth in what's called geosynchronous orbit, meaning that they orbit the Earth's equatorial plane at a speed that essentially matches the Earth's rotation. So this allows them to stay in a fixed position, kind of a specific point relative to the Earth's surface. Now there are, at least over the U.S., there are two satellites always in operation at any given time. One is situated over the Pacific, providing views of Hawaii, the western United States, Alaska. And then there's one situated over the Atlantic, providing a view of the eastern U.S. and the Atlantic Ocean. And they can be stitched together to produce a single satellite image like you see here. So there is a stitch in this. You can't really see it too well, at least not in this particular view, in this visible satellite image. But this is essentially stitched together from two different satellites that you see here. And just as some historical component is that when they launch these satellites, they usually designate them with a specific number. So you may have heard of GOES-R or GOES-S. But once they get to orbit, they change those to numbers. And so currently we have GOES-16, which is over the Atlantic, and GOES-17 over the Pacific Ocean. Now we know that these satellites have essentially onboard sensors, and what they're trying to do, and we look at it from any particular body like the Earth that has some temperature, is going to radiate energy, and in many cases it radiates this energy in multiple wavelengths or frequencies. And these satellites are tuned such that they can pick up and receive these different frequencies. And just like you would have on a radio tuning into various different stations, they can tune into various different frequencies that are from this radiation coming out of the Earth. And as a result of that, they can produce a wide variety of satellite images. Now the most common images you'll see, if you can go to aviationweather.gov and see this as well, are visible satellite images and infrared satellite images. And there's also kind of an offshoot of the infrared, and that is water vapor images. Now in EZWxBrief, we only have the visible and infrared satellite, the color enhanced infrared satellite image, which we'll look at in a bit and we'll focus on. But the visible satellite you see here is just like taking a picture. It's like the satellite is pulling out their iPhone and snapping a shot of the Earth, of what you can see in the visible spectrum of radiation. And this would be the same thing if you're up at 39,000 feet looking at a set of clouds really close to the Earth, like maybe a stratus deck. Again, it's the same kind of a thing. So it's basically the visible satellite image. Now, the problem with visible satellites, there are several, is that they only give you information at night. So essentially, once the sun sets in this area, you'll eventually lose the visible satellite image through the overnight hours. The other one is kind of subtle, but in the wintertime, what you'll notice is that you'll see what looks like and appears to be clouds may actually just be snow on the ground. And you can see other kind of fun things too, like you can see where rivers are located. You can see where valleys are located. And you'll notice over in the western U.S. we have what essentially is some valley fog here showing up. Sometimes you can tell the difference between cumuliform clouds, maybe the high cirrus clouds, and you can also see with a loop, you can see rotation or movement of the clouds. And certainly the visible image, for the most part, other than the whole issue with snow on the ground, is pretty easy to interpret in most scenarios. And this is usually the go-to product of all the satellite images that you'll get. It's the go-to product for the most pilots out there. So the visible satellite image probably is the most useful of all the satellite images out there for the average pilot. Now in this particular case, we can use EZWxBrief to zoom in on a particular area. So let's say if I wanted to go out west and see what's happening with that valley fog in that area, we can actually then find the, let's see, the northwest or southwest. Let's just go to southwest and pick the Las Vegas and see what we see there. And sure enough, you can see that we have a lot of clouds showing here, even some ripples in the clouds that shows the possibility of trapped lee waves. So anytime you see a ripple effect like you see up here in northern Nevada or here in the Salt Lake City area, that most likely means you have some kind of mountain wave activity. And that ripple effect that you see is pretty common even east of the Appalachian Mountains, And again, it indicates you have trapped leeways. They're trapped at a low level, basically just above the mountain peaks in that area. And usually they are lined up right on the, let's say, ridges of the mountains that exist there. They don't always have to be that way, but in most cases that's what happens, and that's the mountain wave effect associated with it. It doesn't mean necessarily you'll be in turbulence or anything like that, but it just, again, indicates that, hey, we've got a mountain wave scenario here. And if we look at this area in California, we can see that that's a low stratus deck. And a lot of times what you can do is look at the kind of the motion of this, and you'll see that the stratus deck is actually shrinking a little bit as you get the heating of the day, and that mixes out a lot of that. So by probably the next 2 or 3 hours, most of this will have essentially mixed out. And also as a result, you can see here where the stitching is. Certainly you can see that's that kind of line that's presented in the satellite image, and it shows up pretty nicely here in this particular case. But that's kind of how they stitched the two products together. So if we then essentially look at these images for the actual visible satellite image, this doesn't give us much information on what height or what the whether these are deep clouds or whether they're up in higher in the atmosphere or lower in the atmosphere. You have to unfortunately look at kind of how they're generated, and certainly this valley kind of fall going on here just to the west of the Sierra Nevadas, so that kind of gives you an indication that it's probably low stratus. And the fact that it's not moving a whole lot like you see the clouds in the southwestern U.S. and into Mexico, you can see how that's kind of moving that way. Those are lower level clouds. And you can also see the same thing with respect to the wave activity up here in Nevada, where you see those clouds are kind of stationary, which again gives you the indication they're probably pretty close to the surface. And then you can see what are essentially very wispy like clouds here in Arizona, and probably associated with some higher level cirrus. And you can even, especially during the let's call it the sunset sunrise time frame, where you get some shadowing, some of that can indicate some of the depth of the clouds, especially when you start dealing with tall towering cumulus or thunderstorms. You'll see a scenario where you'll see some sculpturing to that as well. So this gives you kind of that visible satellite imagery depiction. There's also in EZWxBrief the infrared satellite image, and we'll start with the national level for now. And there are multiple different kinds of infrared satellite images, and they're for different purposes. So I'm not going to spend time looking at all the different kinds of images, but they specifically look at a band of frequencies or wavelengths, to be specific. And the goal is for the researchers that developed all these is to know kind of what this tells us. And the primary job of this infrared satellite image that you see here is to tell you about temperature. And you can see on the bottom there's a scale showing here, and that's in degrees Celsius. And so it's showing you the temperature that the satellite is seeing for the Earth or clouds. So in an area where it's clear skies, where there's no clouds at all, what you're seeing is the temperature of the land or the ocean. And anytime you see these other areas here, you can see, especially if you can see them moving, it's a good idea to kind of animate things, because you can see there's definitely some other clouds that are probably lower, and I'll tell you exactly why I think of that. You can even see that area where we see the valley fog in California. kind of just staying in place in a specific color here, there's a lot that can be gained from this image alone. It's one of my favorites to look at, especially right before I fly, because it can also tell you a fair amount about icing potential and even IFR conditions. So the temperature that you see here, and we know that any object that has a temperature above absolute zero is going to radiate energy. And this satellite, the sensor, is picking up that radiation and then converting that to some temperature. And my understanding is there's a cold bias to this temperature by a couple degrees. So in some cases you may find that where it may be telling you that it's, let's say, 0 degrees Celsius, it may be more like the actual temperature itself might be more closer to +2 Celsius or so. But that's a small detail. So if you compare the colors that you see here with the colors on this particular legend at the bottom, what you're going to notice is pretty clearly that the higher clouds are going to have the bluish and the purple colors representing higher cloud tops, because as you go up in the atmosphere, it gets colder. And some of the highest cloud tops that you may see are likely due to convective elements. Because cirrus clouds generally are somewhere in the order of 25 to 30,000 feet. They can go higher, especially if it's a blow-off from a shearing of a thunderstorm in the distance, but in most cases they're not really way up there in height, so they're not going to be up there in the minus 68 or 70 or even colder cloud tops. Those are going to usually be somewhere in the minus 30s and minus 40s. So anytime you see weather that has this purplish color, and I'll zoom in here a little bit and we'll look at a specific area here in just a bit, certainly that is an indication you've got some deep weather conditions moving into that area. And essentially it could be related to mountain wave activity sometimes, because we can see some of these higher cloud tops basically forming a mountain wave activity, and you can see if I run this over, you can see kind of how it's, you know, almost like that entire line here is really kind of very cut. And so this could be some mountain wave activity that could be working its way up higher. And you have to look at it and then also understand the big weather picture, look at other convective outlooks, look at next route or radar, kind of determine what's going on there. But there's certainly a lot to be gained by looking at this particular diagram. So if we look at what's happening out west, let's say with the stratus layer that's here, we go back out to the southwest U.S. and look at the Vegas radar, or IR I should say, there's our stratus deck. And it has a cloud top temperature that's kind of in this orangish range here, which looks like around 16 degrees Celsius. And if you went to a skew-T diagram, for instance, you could probably figure out where the tops of this are based on understanding what the cloud top temperatures are, and essentially where that skew-T diagram has the tops located. So if I were to look at a specific point in this particular area, it's pretty easy to find a skew-T diagram for that area. The current analysis is a good approach, and then you'll be able to determine where the tops of it. So if you're departing out of an airport IFR, for instance, out of the valley, at that point in time, you're probably going to pop out at some specific altitude, which you can further quantify by looking at something like a skew-T diagram. And once again, you can see on here, it shows up the wave activity, shows up really nice And just because, for instance, you see clouds in this area with waves, you could still have that same wave activity further south. It's just too dry for any clouds to show up in that wave activity overall. And if we scoot to a little bit to the east here and look at the Denver area, we can check this out here. And some really significant cloud cover that has some really cold cloud tops. And let's look at, for instance, and compare that with the visible satellite image in this area as well. Yeah, you can almost see that this is all related to some terrain features here, and more or less because of the standing nature of these clouds. They tend to be kind of fixed in that area. This may be producing some vertically propagating mountain waves to much higher altitudes. But we also have to look at and see what's happening with the next rad imagery to make sure that maybe whether this is something associated with convection. And you can see here, looking at this, that there's not any precip in this area, so this is not convectively driven in this region. Whereas when we're looking at the infrared satellite, it's pretty obvious that this has nothing to do with precipitation per se, and it's kind of spread out, almost like you take a paintbrush and you brush it onto a canvas and see that kind of spread out there. And then you would want to look further at, for instance, and see what pilot weather reports are being reported in this area to sense, is this an area where they're seeing some significant turbulence? And you can either go on to the EZ map and look at pilot weather reports that way, or for instance, I could look at the, let's say, Southwestern pilot reports, and you definitely see some severe reports here, but not much in the way of reports at even higher altitudes. So it would be interesting to see where those clouds, what's actually generating that. Let me go in and take a look at southern plains, look on the other side of this. And there definitely are reports, higher reports of some moderate turbulence in many areas here. And so no doubt that we've got some turbulence aspects in there, and they could be related to some of that wave activity that we see here. Let's go back again and look at the infrared satellite, and I want to go back to the national view. And the last thing I'm going to mention is, I mentioned it in the beginning, that this particular chart is really nice to be able to help you out in terms of whether or not you'll pick up any significant airframe ice. And so we know that airframe ice is usually in clouds. It can be in precipitation, of course, like freezing rain or freezing drizzle, but usually in clouds, and especially those clouds that have warmer sub-freezing cloud top temperatures. So when we're looking at this from the perspective of icing, what we're looking for are cloud top temperatures, and again, I'll look at the legend down here. So we're looking at anywhere that we see temperatures of 0 all the way down to, let's say, as cold as -20 for cloud top temperatures. That's a good indication that you are in a situation where those cloud top temperatures are kind of perfect for icing conditions, because if the tops are at minus, let's say, 15 or minus 12 degrees Celsius, you know that below that the cloud is dominated by liquid water. And so I can extend that to as cold as maybe minus 20. So anywhere you see in this chart here, anywhere you see clouds, and we know they're clouds because you can see them moving, although you have to be careful in the really cold temperatures where the surface of the Earth is at the minus 20 and minus 15 range, you may actually just be looking at the surface of the Earth. Same thing we talked about with snow in the visible satellite image. But nevertheless, if you know that these are clouds, anywhere you see the yellow, light green, or even really, really pale blue colors that are showing up here, you know you're in perfect temperatures for icing potential. And so any of these clouds that have that yellow, maybe even kind of orangey yellow to light pale green all the way through into a very, very light kind of baby blue color, that's where you're going to see the likelihood, because if the cloud top temperatures are on those warmer side, then at that point in time I know kind of the clouds below that are going to be dominated by liquid water. That's a good approach, and it usually works pretty well. But you can see here that you've got some area in Arkansas where the colors are certainly up there in the 12, 13, 14, 15, 16 range Celsius. You're not going to, if you're flying in those clouds, and most likely this is again a kind of a stratus deck in this region, you can check METARs and look at the terminal forecast for future to determine where those clouds may be located in terms of altitude. So this shows me for sure that if I'm flying in an area in those clouds, that I'm not probably dealing with any kind of icing. But when you get into the, let's say, the darker blues, that's going to produce a lot more ice crystals, and those ice crystals can tend to fall through the cloud and essentially turn that cloud over from a liquid cloud to more of a glaciated or mostly ice crystals. So having ice crystals or having cold cloud tops starts to scour out a lot of the liquid in that cloud. And again, it doesn't mean that you won't find icing conditions in the clouds below. It just tends, and I would say just it's really based on a trend that icing probabilities are a lot lower. Again, that's not really true of convective clouds, but non-convective clouds where you have really cold cloud tops, that's essentially what you can expect. And again, it's real important to look at things over historical purposes here, because in the end that's going to tell you more about what's happening there. So let's take a peek at the EZMap, and we'll look at, again, pilot weather reports, and we'll look at the surface observations in that area. So we're set at 21Z, the farthest left, and we're dealing with surface observations here. And if I go out further, and let's go to the western U.S., and we should be able to see in this particular case, yes, those are all the clouds that we see. We're dealing with marginal VFR ceilings and visibility. Here, even IFR conditions. So that's all that stratus deck that's in the valley area. So now we've confirmed, we've looked at two different products, and essentially allows us to better understand what's going on in that area here. And if we look at, for instance, pilot weather reports, I can select those, and specifically looking at turbulence reports. And I'm looking at turbulence reports over the last 24 hours. So if I cut that back to like the last 10 hours, I'm seeing for the most part, most of this is low-level turbulence here, not much in the way of higher-level turbulence. And it's showing mountain wave activity here. But some of that wave activity is getting pretty high up there in the atmosphere due to those colder cloud tops that we see streaming along, especially in that area. I'm kind of surprised not to really see a whole lot of turbulence reports, but this one kind of lends itself to say the turbulence is smooth, but there is a mountain wave plus or minus 40 knots. So it's essentially, you're in the, and that's pretty significant, you're in the downwash or upwash of that wave activity in that region. So this actually confirms for me that you're dealing with some pretty high, this is 43,000 feet, pretty high cold cloud tops in that area and mountain wave activity in that region. And you could even look at, for instance, I could go to RKRTN, for instance. Let's go into the, here I'll put in KRTN, and we'll see if this can come up with the skew-T diagram for that area. And I'll pull that over here. And if we look at what's happening recently, yeah, this looks like a good, especially this one here, looks like a very good vertically propagating mountain wave scenario. And the reason that is you have kind of unstable conditions in the first 5 to 10,000 feet. Then you see the little kind of bend to the right of the temperature line. That's that right at the kind of the mountain peak area. As a result of that, that tends to be a situation where it tends to be the stable layer above that you need for mountain wave activity. But because you have unstable conditions here, all the way up through at least 27,000 feet, that allows that wave to vertically propagate up into the higher flight levels, even as high as 43,000 feet, as we saw in the other pilot report. The other aspect of this is look at the actual directional. Anytime you see the wind barbs lined up like toy soldiers here, that's a good indication, and you've got perfect conditions for mountain waves that vertically propagate. And the other element is to see that the wind speed increases with height. This is not as significant as it can get, but this again shows that the wind speed's increasing with height. And again, that's another characteristic of these mountain waves. So this is how you want to utilize all the different products together to kind of assess what's going on in any particular area. So this is a good analysis, and how in this particular case, how satellite images, whether they're visible or infrared, really help to define what's going on. And that wraps up episode 26 of EZWxChat. My name is Dr. Scott Denstead, and as always, I hope you enjoy the simplicity of EZWxBrief.